Getting started with the OpenAI API in Python. Welcome to your beginner-friendly guide to using the OpenAI API. This lesson shows you how you can talk to advanced AI using code. You will learn the basics, key safety tips, and create simple AI helpers. By the end, you can use Python to access, chat, and explore AI features. Running the cell now. What is the OpenAI API? The OpenAI API is a powerful tool for working with advanced artificial intelligence. It lets your Python code generate text, answer questions, summarize, and even understand audio and images. The API connects your computer to AI models like ChatGPT using simple requests. Anyone can use it to build intelligent apps, creative tools, and much more. Running the cell now. Setting up Python and the OpenAI client library. Before you start, you must install the official OpenAI package for Python. This package lets your code easily talk to the OpenAI API. You can use pip, a tool for installing Python libraries, to do this. Running the cell now. Let us make sure you have the right library. This only needs to run once. Import numpy as np. We set the random seed to 42 for reproducibility. This line will install the official OpenAI package, letting Python use artificial intelligence. Now, Python is updated with the OpenAI library so it can talk with AI models. Running the cell now. This output confirms that the OpenAI Python package and its dependencies are already installed and up to date on your system. Seeing requirement already satisfied means the setup step is complete, allowing your code to seamlessly communicate with the OpenAI API. This ensures you can move forward confidently with the lesson without installation issues. The package is now ready for us to use. Sometimes Python prints warnings that are not important for beginners. This line tells Python to hide extra warning messages. Running the cell now. Here, running the code produces no visible output because it only suppresses warning messages for a cleaner coding experience. This helps you focus on important results by hiding less critical alerts, demonstrating a simple setup step that improves readability when working with the OpenAI Python client. Now you will only see helpful output, not confusing warnings. Let us bring in the tools we need for the rest of our lesson. We import the OpenAI package, so Python is ready for artificial intelligence. This lets us talk to the OpenAI API easily from our code. We also import another package, called OS. It helps us work with settings, like our secret API key. Running the cell now. This code sets up the foundation by importing the OpenAI client and the OS module to access your API key securely. There's no visible output because this step prepares your environment to communicate with the OpenAI API, which is essential before making any requests. Notice how importing the client library aligns with the lesson's goal of getting your Python environment ready for OpenAI integration. Now your code is prepared to access the OpenAI AI helper. Staying secure with API keys. OpenAI requires an API key, which is like a password for your account. You must keep this key safe and never share it inside your code. For these lessons, we already saved the API key securely in the environment. You do not need to enter it or paste it anywhere. Your code will load it automatically each time. Running the cell now. This line fetches your secret API key from a safe place called the environment. We store your unique API key from the environment into a variable named API_key. This key allows you to use the OpenAI API while staying secure. Running the cell now. This code securely loads your OpenAI API key from the environment without displaying it, ensuring your secret is never exposed in your code. Notice there's no output here. This is intentional to keep your key private and protect access to your account. This practice is critical for staying secure when working with API keys. Now your program has access to the AI, but no one else can see your key. Let us make a client object so you can send messages to OpenAI with code. We create a client, which is an object that lets us ask questions or make requests to the OpenAI servers. Now you have a connection that you can use to talk to artificial intelligence in your own projects. Running the cell now. This code initializes the OpenAI client using your securely stored API key, but it doesn't produce any visible output. Notice how the key isn't hard-coded or printed, which aligns with the lesson's focus on keeping your API key safe and confidential while enabling seamless access to the API. The client is ready for you to use. Understanding chat completions. The most popular way to use the OpenAI API is through chat completions. In simple words, you send messages to an AI and get helpful answers. You choose the model, write a question, and receive a smart reply. This is the same core power behind ChatGPT. Running the cell now. Let us see how you can ask artificial intelligence a question and get a response. We call the chat completions feature using our client, which lets us talk with the AI easily. We tell it which model to use. Mini models are efficient and great for learning. We set up our first message, just like you are texting a friend. Now the AI will read your message and answer it. We get the actual reply from the AI. We print what the AI said, so you can see the answer on the screen. Running the cell now. Here, the AI responds to the simple greeting "Hello" with a polite and helpful reply, demonstrating how chat completions work in practice. Notice how the output shows the AI engaging naturally, reflecting the core idea of sending messages and receiving intelligent, context-aware answers using the chosen model. This confirms the API's ability to simulate a conversation, which is central to how ChatGPT functions. You have now sent your very first message to OpenAI's AI and printed the response. Now you can ask the AI anything you like and see what it says. This is a comment explaining you can type a question for the AI. We prompt the user to type their question and save it in a variable. We start calling the AI chat completion method using the client. We specify which AI model to use for generating the response. We format the user's question into a message structure the AI expects. We print out the AI's response to the user's question. Running the cell now. This output demonstrates a typical chat completion where the AI answers the user's open-ended question with a detailed explanation. Notice how the response is structured, informative, and immediately follows the user input, showcasing the real-time interactive power of the chat completion API. This highlights the core lesson intent, sending a user query and receiving a meaningful, context-aware reply from the AI model. This shows how easy it is to chat with artificial intelligence in your own code. Let us ask the AI to explain a key idea for this lesson. This is a comment line introducing the topic, "What is semantic similarity?" We call the AI model's chat completions create method to get a response. Here we specify which AI model we want to use for generating the answer. We send a message to the AI asking it to explain semantic similarity simply. The API returns a response, which we store in the variable's explanation. We print out the text of the AI's response so you can read the explanation. Running the cell now. This output shows the AI's clear and simple explanation of semantic similarity, demonstrating how chat completions provide useful, human-like answers to your questions. Notice how the response is directly relevant and easy to understand, highlighting the core benefit of using chat models like GPT-4.1 Mini to get helpful, context-aware explanations. Now you know what semantic similarity means from the AI itself. What are embeddings and vector similarity? Embeddings turn your text into a list of numbers that the AI uses to compare ideas. These numbers are called vectors, and they help the AI understand if texts are similar. You can use embeddings to match search results, organize data, or cluster meanings. Vector similarity means comparing how close two pieces of text are using math. Running the cell now. Now you will see how text goes from words to numbers for the AI. We use the embeddings feature from OpenAI, which creates vector numbers from your text. We call the create method from the embeddings API to generate embeddings. We specify the model that is designed to produce embeddings. We provide the input text to embed as a list of strings. We extract the embedding vector from the response data. We print the length of the embedding vector to show its size. Running the cell now. This output shows that the embedding vector for the input text has 1536 dimensions, meaning the text is represented as a list of 1536 numbers. Notice how the length reveals the size of the vector space used to compare texts, which is key for understanding how detailed the ARI's representation of meaning can be. This demonstrates how embeddings convert text into structured numerical data for similarity comparisons in machine learning tasks. These embeddings let us compare and match texts by how alike they are in meaning. Next, you will see how computers measure if two texts mean nearly the same thing. This comment explains we will compare the meaning of two short sentences using semantic similarity. Here we define a function named cosine_similarity that takes two vectors as inputs. The docstring describes that this function calculates the cosine similarity between two lists of numbers. We import the math module to use mathematical functions needed for the computation. This line calculates the dot product of the two vectors by multiplying respective elements and summing the results. These lines calculate the magnitude, or length, of each vector using the square root of the sum of squares of their elements. We check that neither vector has zero magnitude to avoid division by zero errors. If both magnitudes are valid, we return the cosine similarity by dividing the dot product by the product of the magnitudes. If either vector has zero magnitude, we return a similarity of 0. We assign the first sentence to the variable text1. We assign the second sentence to the variable text2. This comment explains we are going to get embeddings for both text strings. Here we call the client's embeddings API to create embeddings for the input texts. We specify the embedding model to use, named textEmbedding3 small. We provide both text1 and text2 as input in a list to be embedded together. We extract the embedding vector for the first text from the response. We extract the embedding vector for the second text from the response. This comment explains we will show the similarity score between the two embeddings. We calculate the similarity score by passing the two vectors to our cosine_similarity function. We print the rounded similarity score in a friendly format. Running the cell now. This output shows a similarity score of 0.64, meaning the AI found a moderate level of closeness between the two sentences about cats and felines napping warmly. The score, calculated using cosine similarity on their embeddings, reflects how the AI represents meaning in vector form and compares these vectors to measure text similarity. This connects to the lesson by demonstrating how embeddings and vector math help quantify how alike different pieces of text are. This is the key idea behind searching, organizing, or deduplicating texts with artificial intelligence. How can you use similarity in real life? Semantic similarity helps you find duplicate questions, cluster users by their interests, or even build smarter search engines. Vector-based tools are more flexible than exact keyword matching. You can power up chatbots, study documents, or analyze feedback meaningfully. Running the cell now. Let us build a small project that can answer help questions by matching to the closest FAQ. First, we make a list of possible questions that your website might frequently get. These are called frequently asked questions or FAQs. Here, we define a list called FAQs containing example common questions users might ask. The first FAQ, how do I reset my password? The second FAQ, what are your working hours? The third FAQ, Where can I update my email preferences? The fourth FAQ, how can I contact support? We close the list of FAQs. We prompt the user to type a help question that they want answered. We create a combined list containing the user's question followed by all the FAQs. We call the embedding model to create vector representations for all texts at once. Specify which embedding model to use, text embedding the 3 small. Pass the combined list of texts to the embedding API. Retrieve the embedding vector corresponding to the user's question. Make a list of embedding vectors for each FAQ question. We calculate the similarity score between the user's vector and each FAQ vector. Find which FAQ has the highest similarity score to the user's question. Print the FAQ that is identified as the best match for the user's query. Running the cell now. This output shows the FAQ question most semantically similar to the user's input, highlighting how the model matches meaning beyond exact words. Notice that the highest similarity score corresponds to the closest related FAQ, demonstrating how embeddings help find relevant answers in a set of options. This approach powers smarter search and support by understanding user intent rather than relying on keyword matches alone. You have now created a mini AI-powered search for matching questions by meaning, not just words. Sometimes, a user's question might not match any stored answer closely. Explain the scenario where no strong match might be found. Prompt the user to enter another question for a second attempt. Create a new list combining the new question with the FAQ list. Start creating embeddings for the combined texts using the client. Specify the embedding model to use as text embedding 3 small. Pass all the combined texts as input to the embedding model. Retrieve the embedding vector for the user's new question. Extract the embedding vectors for each FAQ item from the results. Calculate cosine similarity scores between user question and FAQs. Find the best, maximum, similarity score from all scores. Check if the best similarity score is greater than 0.5 threshold. If it is, print out the FAQ that corresponds to the best score. Otherwise, inform the user that no close match was found. Running the cell now. This output shows what happens when the user's question doesn't closely match any FAQ based on semantic similarity scores below the 0.5 threshold. Notice how the code uses vector embeddings and cosine similarity to quantify closeness, and only returns a match if the score is sufficiently high, ensuring relevance. This approach highlights how vector-based similarity can effectively filter out unrelated queries, making search or chatbot responses more precise and meaningful. This check helps your tool avoid giving users the wrong answer just because it is the closest option. Sometimes, you may run into errors, like if you ask the API too many questions, too fast. This line is a comment explaining we will handle API rate limit errors. Start a try block to attempt the following code safely. Call the chat completion creation method on the client object. Specify the model to use for the chat completion. Provide the input messages as a list with a user role and test content. Close the method call parentheses. Print the generated response from the model's output. If any error occurs, catch it here to prevent a crash. Print a message indicating an error occurred along with the error details. Running the cell now. This output shows a successful response from the API despite testing the rate limit, indicating no error was triggered. In the context of using similarity tools in real life, this demonstrates how robust error handling ensures your application remains responsive, even when external service limits are reached. Noticing the friendly, fallback message highlights the importance of graceful degradation for better user experience. By catching errors, your apps will be more friendly and not break in front of users. It helps to pick a model size that matches your task. This comment suggests using smaller models when you can, as a best practice. This line assigns the name of a small model to the variable small_model. This line assigns the name of a larger, more capable model to the variable large_model. This line prints a message advising when to use small versus large models. Running the cell now. This output reinforces a best practice in model selection by emphasizing when to use smaller versus larger AI models. It highlights that smaller models like GPT 4.1 mini are ideal for quick tests to save time and resources, while larger models like GPT 4.1 are better suited for handling more complex questions. This guidance connects directly to using semantic similarity efficiently in real-life applications by balancing performance with computational cost. This saves you credits and gives you fast results when learning or testing. Now you try. Enter 3 different phrases to see how closely the AI thinks they are related. This is a comment describing the challenge to try 3 similar phrases and check their similarities. Ask the user to type the first phrase and store it in sentence 1. Ask the user to type the second phrase and store it in sentence 2. Ask the user to type the third phrase and store it in sentence 3. Put all 3 sentences into a list called input_list. Call the Embeddings API to create embeddings for the input list. Specify the model name to use for generating embeddings. Pass the list of sentences as input to the embedding model. Get the vector embeddings from the response for each sentence. Start a loop to iterate over the first sentence index, 0 to 2. Start a nested loop to iterate over the second sentence index after the first. Calculate the cosine similarity between the 2 sentence vectors. Print the similarity score rounded to 2 decimal places, labeling which pair it is. Running the cell now. This output shows the similarity scores between 3 user-provided phrases, with values closer to 1 indicating higher semantic similarity. Notice that phrases 1 and 2 have a moderate similarity, 0.55, while both have low similarity to phrase 3, 0.26, illustrating how vector embeddings capture meaning beyond exact keyword matches. This demonstrates how embedding-based tools help identify related content, enabling smarter search or clustering in real-life applications. Experiment with different topics or similar words to see how meaning is measured by vectors. For this challenge, enter a text about something totally different from your FAQs. This comment explains that we will try a random phrase to see if it matches an unrelated FAQ. We ask the user to enter any random topic as input. We create a list combining the user's input with the existing FAQs for comparison. We request embeddings for all these texts using the specified embedding model. We specify the embedding model to be used for generating the vectors. We provide the combined list of texts as input to the embedding model. We extract the embedding vector for the user-entered text, the first item. We extract embedding vectors for all the FAQ entries, all items except the first. We compute similarity scores between the user's input vector and each FAQ vector. We print the FAQ entry that has the highest similarity score to the user's input. We print the highest similarity score rounded to 2 decimal places. Running the cell now. This output shows the result of comparing a random input phrase to a list of FAQs using semantic similarity. Notice the very low similarity score, 0.11, indicating the input is quite unrelated to any FAQ, which highlights how vector embeddings capture nuanced meaning rather than exact keyword matches. This demonstrates how similarity models can effectively identify relevant or unrelated content, powering smarter search and matching in real life. Understanding how scores drop for unrelated ideas helps you trust AI for filtering and clustering. Recap: you have learned the basics. You can now connect to the OpenAI API, send chat prompts, and get generated answers. You explored embeddings and vector similarity to compare how much meaning 2 texts share. By combining these skills, you can build creative and helpful AI applications. Running the cell now. Keep exploring and subscribe for more. Try changing the model and repeating the challenge exercises above. Experiment with different questions or build your own FAQ lists. Practice makes you more comfortable with AI and code. Subscribe for more beginner tutorials and projects. Running the cell now.